Good morning, champs. Today we're solving our first simply supported beam with a distributed load. In the previous videos, we worked with cantilever beams. Although the loading method remains exactly the same, changing the support conditions leads to very different internal force diagrams. Consider a beam that is 6 meters long. The beam is supported by a pin at the left end and a roller at the right end. A uniform distributed load of 4 kilonewtons per meter acts over the entire length of the beam. Our goal is to determine the internal axial force, shear force, and bending moment. As before, we begin by calculating the support reactions. The total equivalent force is the load intensity multiplied by the beam length. 4 kilonewtons per meter acting over 6 meters gives a total force of 24 kilonewtons. Because the load is uniform, this equivalent force acts at the center of the beam. Taking moments about the left support gives a right support reaction of 12 kilonewtons. Applying vertical equilibrium then gives a left support reaction of 12 kilonewtons. There are no horizontal loads, so the horizontal support reaction is 0. Now we make a cut at position X and keep the left-hand segment. There are no horizontal loads, so the internal axial force is 0 everywhere along the beam. Next, we determine the shear force. The equivalent distributed load acting on the left segment equals the load intensity multiplied by the length of the isolated segment. Applying vertical equilibrium gives the shear force function equal to 12 minus 4x. At the left support, the shear force is positive 12 kilonewtons. At the middle of the beam, the shear force becomes 0. At the right support, it reaches negative 12 kilonewtons. Now we determine the bending moment. The equivalent distributed load acts at the midpoint of the isolated segment, so its lever arm is x divided by 2. Applying moment equilibrium gives the bending moment function equal to 12x minus 2x squared. Notice that the bending moment is 0 at both supports, exactly as expected for a simply supported beam. The largest bending moment occurs where the shear force is 0. Setting the shear force equation equal to 0 gives x equals 3 meters, which is the center of the beam. Substituting this position into the bending moment equation gives a maximum bending moment of 18 kilonewton meters. The most important lesson from this example is that the loading has not changed, but the support conditions have. Those support conditions completely change the support reactions and, as a result, the internal force diagrams.